We're going to start section 7.1, which is about sample means, the t-distribution, and the central limit theorem. Suppose the weight of all golden hamsters is normally distributed with a mean of 120 grams and a standard deviation of 15 grams. My first question to you is, what do I mean by all golden hamsters? That is, how large is the population? So what I mean by all golden hamsters is all golden hamsters to have ever or will ever exist. Now we have no idea how many hamsters that is, and it's impossible to know the true mean weight in reality, but we're going to assume that it's 120 grams. Now, if the true mean is 120 grams, what's the probability of getting a hamster that weighs between 105 and 135 grams? We've done problems like this before. We know the distribution is normal. It's told to us in the problem. So let's figure out how far away 105 and 135 are from the mean 120. And notice that both of those numbers are 15 grams away, which means that's one standard deviation, below the mean and one standard deviation above the mean. So according to the empirical rule, we know that about 68% of the data is within one standard deviation of the mean. Now, what's the probability of getting a hamster that weighs between 90 and 150 grams? So let's figure out how many standard deviations from the mean these two numbers are. 90 is 2 standard deviations below the mean, so its z-score is -2, and 150 is 2 standard deviations above the mean, so its z-score is +2. And the probability of getting a hamster with a z-score between -2 and 2, we know from the empirical rule, it's about 95%. Now, if I collect a sample of 100 hamsters and I weigh them all, then 95% of the time, the sample mean should be between what two numbers? Notice how this problem is different from the last problem. In the last problem, let me go back. We're talking about a hamster, one hamster. In this problem, we have collected 100 hamsters, and what we're going to do is we're going to find the average. So recall the average of a sample, we call it X bar, sample mean. We add up all the weights of those hamsters and divide by the total. So I'm going to weigh 100 hamsters, find their weights, and then divide by 100. This formula includes all the data in the sample. So let's see what will happen if we run a simulation. What I'm going to do is I'm going to go into Microsoft Excel, and I'm going to ask Microsoft Excel to pick 100 hamsters. So we know from the last problem that 95% of the time, our hamster weights should be between 90 grams and 150 grams. So we're going to take a look at our 100 hamsters and just kind of eyeball it and see if all of those weights are kind of between 90 and 150. And then we're going to average all of those weights and see what kind of number we get for the average. Is it going to be somewhere between 90 and 150, or is it going to be closer to the actual mean, 120 grams? So here's the code we're going to use, equals norm.inv rand 12015, and we're going to copy that into 100 cells. I'm going to put it into A1, and I'm going to drag it all the way to A100. Then underneath somewhere, we're going to type equals average A1 through A100. Okay, so here I am in Microsoft Excel. I'm going to type equals norm.inv rand, 120, 15. Here I've selected one random hamster, and its weight was 128 grams. Now I'm going to go to the bottom right-hand corner, and I'm going to drag this all the way down to A100. Now let's take a look at the values we got. Start at the very top. So I got 112, 118, 137. Remember that 95% of the time we said that we expect a hamster to weigh between 90 grams and 150 grams. And so far, here's our first one that's not between 90 and 150 grams. But the majority of these, scrolling down, here's another one that's not in between. But you can see the majority of these values are between 90 and 150 grams. Okay, I'm going to go down to 102, cell A102, and I'm going to type equals average. I want to average A1 to A100. And so let's think about what we will get. Now we're averaging 100 different hamsters. Do we think we're going to get a number close to the true mean? Remember that the true mean was 120. And I got 117.9. So that's a little ways, not too far. It's definitely not as far as some of these scores. Like 109 is much further away from 120 than this 117 or 94. And then I have up here 136. So you can see that there's more variation in the actual hamsters themselves, but when you average them all together, it looks like we're kind of reducing that variation and bringing it closer to the true mean. Let's try this again. I'm going to copy this cell over, and every time I copy something, it's going to rerun all of these equations, and that's okay. We're just going to get, you can see that all the numbers changed. It's just picking a new random number, but I'm going to drag this down all the way down to 100 again. Okay, and now I'm going to copy this average. So what I've done now is I've created a second sample of 100 hamsters. I want to have a better idea of what kind of values I'm going to get for the mean. So you can see that I have 100 hamsters again. It reran the left side of 100 hamsters, and now I have a second sample of 100 hamsters, and let's look at both of these numbers. Both of these numbers are about 118, 119, which is pretty close to the mean. So what I'm going to do next is I am going to rerun this simulation. I'm actually going to make 130 samples, 130 samples of 100 hamsters. And I want you to see what kind of numbers we get for the average. Are these numbers going to be close to the mean? They're going to be far away? Is it going to be similar to the hamsters themselves? Are we going to get 95% of the time numbers between 90 and 150? Or are we going to get something closer to the mean? Okay, you should see a lot of numbers here. So we have, if we scroll down, here is column A. Here's the first sample of 100 hamsters. In A102, we have the average weight of those 100 hamsters. Okay, and then you can see I just copied the same thing here and I ran it 100 times, and that will be my second sample. And if you go this direction, you can see that I've done it a lot. I've actually done it 130 times. Now let's take a look. I'm going to scroll down to these averages way down here. So these are the averages of each one of those samples. So for the first one, I got 118.57. For the second one, 119.51, 120, 120, 120, 118, 121, 121. I'm just scrolling through real quick so you can have an idea. Let me zoom in a little bit. Look at all these numbers. Notice how much closer they are to the actual mean. So I'm going to create a histogram. I'm going to take all of these numbers and just make a histogram of my results. Let's see what we get. So here is my histogram. Remember that I have 130 samples of 100 hamsters. So 100 hamsters in each sample. And then I counted how many times certain numbers showed up. Between 115.91 and 116.82, it looks like I had one sample that had an average of a number in between those two values. And then maybe 4 or 5 samples had an average between 116.82 and 117.73. We can see that the tallest column here is between 119.55 and 120.45. And the true mean, we're told in the problem, is 120, which is in that tallest column. And looking at that histogram, it looks like a normal distribution. Now, this is not individual golden hamsters. This is the average of 100 hamsters. So we have 130 averages. And let's talk about how wide this normal distribution is. When we talked about just sampling one hamster, we said that 95% of the time, the hamster will weigh between 90 and 150 grams. Let's look at this distribution and eyeball what 95% of the graph looks like. I would say something like this. That looks about like 95%. And let's check out the numbers, the bounds that I have created. The left bound, 117, and the right bound, about 123. Now, unlike when we were sampling individual golden hamsters, we said 95% of the time it was between 90 and 150 grams. This time we're much closer. We're between 117 and 123. So this is a normal distribution that's separate from the original distribution of golden hamsters. It has the same mean, but the standard deviation is different. How do we calculate the standard deviation of the normal distribution that's associated to the sample mean? What do you think is a part of that calculation? Well, definitely it has to be related to the actual standard deviation involving the hamsters, so the 15 grams. But also maybe it should be related to the size of the sample. If we have a bigger sample, you would think that the average weight would be closer to the true weight of 120 grams. The smaller the sample, there could be more variation, and so it wouldn't be as close. So what will affect how close the sample mean is to the true mean? The sample size. So the larger the sample size, the closer the sample mean will be to the true mean. And the standard deviation of the population. The larger the standard deviation, the further the sample mean will be from the true mean. So here's the central limit theorem for the sample mean. It says when we collect a sufficiently large sample of n independent observations from a population with the true mean mu and true standard deviation sigma, the sample distribution of x bar will be nearly normal, where the mean is mu, but the standard deviation is different. We call this the standard error, and it's sigma divided by the square root of n. Now notice we said we needed independent observations. What does that mean? We need to check to see if the sample has been chosen using simple random sampling. That's usually told to us in the problem. And we also mentioned sufficiently large. Now this type of problem is different from proportions. The mean is not p, it's mu. It's not a percentage, it's a measurement. So what do we mean by sufficiently large? For us, whenever we have a sample size that's greater than or equal to 30, that will be sufficiently large. Now, if you happen to have a sample that's less than 30, but there are no clear outliers in the data, then we can assume the data comes from a nearly normal distribution. Now let's go back to that question where we have golden hamsters with a mean weight of 120 grams and a standard deviation of 15 grams. If I collect a sample of 100 hamsters and weigh them all, 95% of the time, the sample mean should be within what two numbers? So 95% of the time is about 2 standard deviations away from the mean. To be a little more exact, we could use the z-table, and it's 1.96 standard deviations away from the mean. Let's calculate our standard error, which for our sample mean is sigma divided by square root n. That's 15 over the square root of 100. which gives us 1.5. So we're going to take our z-score, because we want 95% of the time. The z-score is 1.96, and we're going to multiply by the standard error here, which is our new standard deviation, and we get 2.94. We add it and subtract it, we'll get 117.06 and 122.94. Remember in that histogram, and you can go back a little bit in the video, I said when I eyeballed the 95%, I said the numbers were about 117 and 123. And these two numbers validate that. Let's try another problem. If I collect a sample of 100 hamsters and weigh them all, what's the probability the sample mean is greater than 117 grams? Well, I'm looking for the probability x bar, not x, but x bar is greater than 117. Let's convert that to a z-score. The z-score is the difference between our statistic and the true mean divided by the standard deviation. So we're going to take x bar, 117, subtract mu, and divide by our standard deviation for this particular normal distribution. And we get -2. So the probability x bar is greater than 117 is the probability z is greater than -2. So pull out your z table, look for -2, or you could use Microsoft Excel, but just remember that the z table in Microsoft Excel gives us the probability z is less than -2, and you have to subtract it from 1. So double check that you can get the correct final answer, which is 0.977. So there is about a 97.7% chance that the sample mean will be greater than 117 grams. I want to go back to the slide with the central limit theorem, and I want to circle something. Notice that it says we collect a sufficiently large sample of n independent observations from a population. It didn't specify what type of population. It didn't say the population had to come from a nearly normal distribution. So that means the population can come from a uniform distribution or a skewed distribution. For example, suppose we roll a die 100,000 times. Let x represent the number we roll. What type of distribution does x have? The probability of rolling a 1 is the same thing as the probability of rolling a 2 or rolling a 3 and so on, and that's 1 out of 6. Now, if we actually did an experiment where we rolled a die 100,000 times, we'll see that our distribution will look very similar to the theoretical distribution. We might have a few more 1s than we do 2s, and a few more 2s than we do 3s, and so on. But with enough rolls, we'll get something that looks like the theory. It looks like a uniform distribution. Now, what is the average of our rolls? If we roll a die 100,000 times, the average should be about 3.5, which is the theoretical average, the expected value. But let's say we roll a die 30 times, and we find the average of those 30 rolls. What kind of distribution do you expect x bar to have? Will it be uniform? No, the central limit theorem tells us it's going to look like a normal distribution. So if we're just talking about x, it's going to have a uniform distribution, but when we talk about x bar, we're averaging different x's together, 30 different x's, averaging them, that's x bar, and what we'll get is a normal distribution where mu is equal to the expected value, 3.5, and the standard deviation is the standard deviation of the uniform distribution divided by the square root of n, where here n would be 30. Suppose a researcher is interested in the average age of citizens of a developing nation. In this nation, education and healthcare is limited. There are high fertility rates and low life expectancies. Suppose the true average age of this nation is 27. If x represents a citizen's age, what type of distribution do you expect x to have? Well, we would expect the distribution to be right skewed. It would have a right tail. Because it has high fertility rates and low life expectancies, we would think the majority of the citizens would be young, and then there would be a few people who live to a long life. Now, suppose you sample 200 citizens of this developing nation and find the average age of the sample, which we call X bar. What type of distribution do you expect X bar to have? That distribution will be nearly normal, according to the Central Limit Theorem. And the mean of that distribution will be around the average age of the skewed distribution. We said that the skewed distribution's average age was 27. If you look at the nearly normal distribution, the average is 27. So in general, the central limit theorem tells us that no matter what the shape of the population is, left skewed, right skewed, uniform, normal, whatever the shape of the original distribution, the distribution of the sampling distribution, the distribution of X bar will be normal as long as n is sufficiently large. And that means n needs to be bigger than 30.